Good day, G10. Welcome again to Mathematics 10A. For today's video, we will be discussing lesson number 6, angles formed by tangents and secants. Before we start, these are the targets for our discussion. First, illustrate secant and tangent line. Second, prove theorems on secants and tangents. To give you a hint about our discussion, let me present to you a real-life application. The sun's rays hit the earth such that the tangent rays determine when the daytime and nighttime are. The time in the earth's rotation determine when certain locations have sun. If the arc that is exposed to sunlight is 178 degrees, what is the angle at which the sun's rays hit the earth? The problem given is a simple application of the tangent line in real life. As you go through this lesson, try to answer the posted problem and ponder on this question. How do the different geometric relationships involving tangents and secants of a circle facilitate finding solutions to real-life problems and making wise decisions? Before we start discussing the angles formed by tangents and secants, let us have first these preliminary concepts. Given a circle, lines could be drawn in such a way that it is coplanar to the circle. Figure 6.1 shows the different cases by which those lines and the circle could appear on a plane. On case 1, line ED does not intersect circle A, while on case 2, line FH intersects circle B at exactly one point only. On the third case, line IJ intersects the circle at 2 points. In this module, we will be focusing on the type of lines shown on cases 2 and 3. Case 2 of figure 6.1 illustrates a tangent line. A tangent to a circle is a line coplanar with a circle and intersects it in one and only one point. The point of intersection is called the point of tangency. In the figure, line FH intersects circle B at point G. Line FH is a tangent line and G is the point of tangency. We already know that a segment is a subset of a line. Now, we will be having a subset of a tangent line, which is the tangent segment. It is a segment which is a part of a tangent line, and one of its endpoints is the point of tangency. In reference with the figure, segment FG and HG are tangent segment of circle B. And as you can see, point G is the point of tangency, wherein both segments has it as its endpoints. We have different kinds of tangent line in relation to two or more circles. We have the so-called common tangent. Common internal tangents intersect the segment joining the centers of the two circles. Given the figure, we have line EF and line GH as common internal tangents of circle A and circle C. These two lines intersect the segment joining the center of the two circles. The other type of the common tangent is the common external tangent. It does not intersect the segment joining the centers of the two circles. In the figure, we have line IL and line JK as the common external tangents of circle B and circle D. These two lines does not intersect segment BD. Going back on figure 6.1, case 3, it illustrates a line that is drawn again coplanar to the circle. Specifically, it illustrates a secant line. A secant is a line that intersects a circle at exactly 2 points. A secant contains a chord of a circle. On the figure, line IJ is a secant line and line segment IJ is a chord of the circle contained on the given secant line. Like a tangent line, a secant line has its subset, which is the secant segment. It is defined as a segment which intersects a circle at 2 points, and only one point of this is an endpoint of the segment. In the figure, segment IK is a secant segment of circle D. As you can see, point I, which is one of the endpoints of the secant segment, lies on the circle, and point K, another endpoint, lies at the exterior of the circle. Another set of preliminary concepts to be discussed are the so-called postulate and theorems on the tangent line. Starting first with the tangent line postulate, we have this figure. At a given point on a circle, one and only one line can be drawn that is tangent to the circle. Again, on the figure, if G is a point on the circle, then one and only one line can be drawn through G that is tangent to the circle. And as you can see, G is the point of tangency. This just states that if we are to draw another line which is steeper than the given line, it will not be tangent to the circle at point G. Another case is that if the line is a little less steep than the given line, then it might be tangent to the circle, but again, not at point G. Next, moving on to the tangent line theorem, we have this figure. Take note that this theorem has two parts. The first one is that if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. To illustrate, let us have the figure. If line MN is tangent to circle O, then it is perpendicular to segment OP. And take note that segment OP is a radius of circle O. The second part of the theorem states that if a line is perpendicular to a radius of a circle at its endpoint that is on the circle, then it is tangent to the circle. It is also called the converse of the tangent line theorem. To illustrate, let's have again figure 6.5. If line MN is perpendicular to segment OP at P, then line MN is tangent to circle O. Now at this point, we will be discussing the theorems on angles formed by tangents and secants. Intersecting secants and tangents form angles whose measures are related to the measures of the intercepted arcs. Here are three ways for those lines to intersect through a given circle. Case 1, the lines may intersect at the exterior of the circle. Case 2, the lines may intersect on the circle. And in the third case, the lines may intersect at the interior of the circle. The angles formed by these three illustrations are all at the exterior of the circle. And to give you the relationship among the angles formed and its intercepted arcs, let us have this theorem. If two tangents, a secant and a tangent, or two secants intersect at the exterior of a circle, then the measure of the angle formed is 1/2 the positive difference of the measures of the intercepted arc. Meaning to say, we have to subtract the measure of the smaller arc from the measure of the larger arc, then divide it by 2. And that will be the measure of the angle. Taking this example, we have a figure below wherein line QK and line QH are two tangents intersecting outside the circle at point Q. Arc HJK and arc HK are two intercepted arcs of angle KQH. To solve for the measure of angle KQH, we have to subtract the measure of arc HK, the smaller arc, from the measure of arc HJK, the larger arc, and then divide it by 2. As you can see, the two lines just divide the circle into two parts, which are the major arc HJK and the minor arc HK. Now, if the measure of arc HJK is 250, then we may say that the measure of arc HK is 110. Now, to solve for the measure of the unknown angle KQH, we have 250 minus 10 multiplied by 1/2, which gives us the measure of angle KQH, which is 70. Another example is the given illustration, wherein a tangent and a secant intersect outside the circle. In the figure, line CM is a secant and line LM is a tangent, intersecting outside the circle at point M. Arc LEC and arc LG are two intercepted arcs of angle LMC. These two arcs will be used to solve for the measure of angle LMC. So the working equation will be the measure of angle LMC is equal to 1/2 multiplied by the difference of the measure of arc LEC and the measure of arc LG. For example, if the measure of arc LEC is 186 and the measure of arc LG is 70, then we may solve the measure of arc LMC as 1/2 multiplied by 186 minus 70. So we have the measure of angle LMC equals to 58 degrees. And last, for the first case, we have two secants that intersect outside the circle. Given the figure, we have line NX and line MY2, which are two secants intersecting outside the circle at point P. Therefore, we have the measure of angle XPY is equal to 1/2 of the difference of the measure of arc XY and the measure of arc MN. Again, take note that you have to subtract the smaller arc from the larger arc. So given that the measure of arc XY is 140 and the measure of arc MN is 30, then we may solve the measure of angle XPY as 140 minus 30 multiplied by 1/2, which will give us the measure of angle XPY, which is 55 degrees. For case 2, we have two illustrations wherein the first one, a secant and a tangent intersect on the circle, and another one, we have two secant lines that intersect on the circle. The second illustration gives us the inscribed angle theorem, which has been discussed on the previous lesson. So therefore, we will be focusing on this first illustration. If a secant and a tangent intersect at the point of tangency, then the measure of each angle formed is 1/2 the measure of its intercepted arc. To further discuss the given theorem regarding the angles formed by secant and a tangent, let us have the figure, wherein line QS is a secant line and line RW is a tangent line, which intersect at point S, which is on the circle. Arc QS is the intercepted arc of angle QSR, and arc QTS is the intercepted arc of angle QSR. So as you can see, there are two angles that are formed in this case. To solve for the measure of angle QSR, we will be using the measure of arc QS. If arc QS is 170 degrees, then we may say that the measure of angle QSR is equal to 85 degrees. While for the measure of angle QSW, we have 1/2 of the measure of arc QTS. If the measure of arc QTS is 190, therefore the measure of angle QSW is equal to 95. For case number 3, wherein lines intersect at the interior of the circle, there are two secant lines that are drawn through the circle. And this theorem states that if two secants intersect at the interior of the circle, then the measure of the angle formed is 1/2 the sum of the measures of the arcs intercepted by the angle and its vertical angle. In the figure below, line WS and line RX are two secants intersecting inside the circle. As these two lines intersect, there forms four angles: angle 1, 2, 3, and 4. Angle 1 and angle 3 are pairs of vertical angles, while angle 2 and angle 4 are another pair of vertical angles. For us to take the measure of each angle, take note of the idea of vertical angles wherein those pair of angles are congruent. Let us try to solve for the measure of angle 1. And with this, we will be using the measure of arc WR, its intercepted arc, and arc XS, the intercepted arc of angle 3. We will be using the working equation, which is the measure of angle 1 is equal to 1/2 of the sum of the measures of arc WR and arc XS. So for example, if the measure of arc WR is equal to 100 and the measure of arc XS is 120, then we may solve for the measure of angle 1, which is equal to 1/2 of the sum of 100 and 120, which will be equal to 110. While solving for the measure of angle 2, we will be using the formula. The measure of angle 2 is equal to 1/2 of the sum of the measures of arc WX and arc RS. If the measure of arc WX is 80 and the measure of arc RS is 60, then the measure of angle 2 is equal to 80 plus 60 divided by 2, which is equal to 70. That will be all regarding the angles formed by tangents and secants. Thank you for listening, G10. For your questions, reserve it on our synchronous session. Good day again and God bless.